questions first before I get going about any of the problems or?
Could you go over the extra problem you gave?
Yeah. Why don't you? Well, I might be wrong about this. I hope I am, but I don't see any rain in the forecast this weekend. 2, 4, 6, 8, 10, 11, 12. They're coming. 13. Here comes the trend. 14. Go ahead, Andrew.
An antenna radiates in field in free space far field, given as.
Hold on for 1 second. So we've got an antenna, it's got a certain transmitter power. Just give me 1 second, Andrew.
All right.
Or maybe it doesn't. All right, we're at a distance r, and now we have a electric field.
Yes.
This is a great problem, guys. Go ahead.
It's given as 20 times I naught cosine theta e to the negative j 60 pi r over r, or the whole thing's over r.
Overall. Yeah.
And then
A theta. And what do they want?
So also I naught given as 2 amps. And they want the frequency and wavelength.
Let's stop there. We're gonna want. Y'all hear this? Now I assume everybody looked at this. There's a quiz today. You'd be foolish not to. First thing you notice is they're asking for F. Well, it's in free space, isn't it? Air, somewhere I say something like that, correct? If it's in air, and you look at this, you can tell it is in what domain? Phasor or time? Phasor domain, right? There is no time variable, right? If it's in the phasor domain, now is it at a given frequency? It must be, or we wouldn't have this. Do y'all follow me, class? So now we look at this. We know all the phasor terms have a form for a propagating wave of e to the minus j beta r. Y'all hear me? I sent this to everybody, but I want to make sure. So therefore, beta is equal to 60 pi. Correct. What is beta? Well, beta, we can do it a lot of different ways. We can fundamentally say what? That 2 pi times beta is the wavelength. Do you agree with that? I'm going to go through, I'm trying to make sure you understand. This is more fundamental because I know this is what's inside that cosine argument, right? When instead of 2 pi it's 0, cosine is 0, 0. Then it repeats itself when the cosine argument is 2 pi beta, right? And, sorry, let me do it this way. I'm sorry. I'll put 2 pi here. I'm sorry about this. That's beta times lambda. Lambda is 2 pi over beta. I wrote that backwards. Are y'all with me, class? Now, I know that, and I know beta, so it's 2 pi over 60 pi is equal to 1 over 30 meters. Hey, Jonathan, you sent me an email, I think. Y'all with me? I got that. I'm in free space. What is the wavelength in free space? C over F, correct? I'm just trying to make sure that I'm not missing anything with you. Sometimes there's one small gap that messes everything up for people. And I can't always tell what it is, so I'm going to go through this. So now what is F? Well, F is C over lambda, 3 times 10 to the 8th over lambda, which is 1/30th. And I don't know, what is that? 90 gigahertz or what?
9 gigs.
9 gigahertz, I'm sorry, 9 gigahertz. 9 gigahertz. What else, Andrew?
And then they ask for the H field in the next part.
All right, now, is it a propagating wave? Yes. Did I say far field? I must have
Yeah,
said
it's far field.
far field. By looking, which way is it propagating? Let's just do this. Which is the direction of propagation? Just take one look. Hint, it has to do with the argument of the exponential. It's in the positive AR direction. Do you agree with this, class? I'm going to do it this way. I know it's AR. Now we could do what? We could say H is equal to 1/8 right? Unit vector and direction of propagation across E. Couldn't we do it that way? It's propagating, right? It's a plane wave propagation. I mean, it's actually not planar. It does have some curvature, but the curvature is of no value if you get far enough away. Now, follow me on this. The way I get this, I know E cross H is the direction of propagation, correct? We could do it with that. If I know E cross H is the direction of propagation, E is in the, what, the theta direction, right? I'm trying to do this. Which way is H? Let me just do this. So if I look at this, I have a positive E field. If this is, I hope this is helping. If this is R and this is theta, I have an E field in this direction, right? Y'all agree with that? Now I know that E, right, crossed in the H field has to be the direction of propagation. Do you all agree with that? All right. That means the direction of H has to be into the board, correct, class? Can everybody see that from the way I drew it? I put the R vector in the plane of the board. So the E field would be going this way if it's A theta direction. Do y'all follow me? In order for E cross H to be the radial direction, because that is a direction of propagation, the E field in the plane of the board would be into the board, right? The way you think about this, this would be the x-axis coming out of the board. This would be the y-axis, and this would be the z if we superimposed a Cartesian coordinate system on spherical coordinates. Do you all see this, class? In the back there, can you guys, Jonathan, you follow me on this? All right, so if H is in the direction of the board, it's into the board, right? And in spherical coordinates, which direction would that be? Remember, in spherical coordinates, you got phi measured from here, and A phi circles around. If you look down the z-axis, A phi is going this way, right? Can you follow me or not? If you look in the plane of the board, A phi is in the minus, what, minus x direction, isn't it? That has to be the direction of H. Do y'all follow me on this, class? Can you see this, sir? I hope I'm being clear about this. Sometimes the visualization is the tough part. So I know that my H field right here is just going to be that E field, well, it's 20, right? I naught. And then I'm going to divide this by eta naught, and eta naught is equal to 125. Didn't I put these answers down, by the way? All right, what, y'all with me? And then you got to put R down here. It doesn't matter if it's small or capital, as long as you know what you're talking about. Then it's going to have the same cosine variation, has to. Magnitude-wise, it won't change in terms of its general signature shape. It'll have the e to the minus j65r, and it will be in the A phi direction. A lot of times spherical coordinates take a little while to get a handle of.
So it's in the A phi direction because you're crossing R and theta.
E, no, not R, E. Remember, E, the E field's in theta direction. Some people don't have a good appreciation of this. If you think about spherical coordinates, and I'm going to put this as x out of the board, this y, and this z. In spherical coordinates, this is the angle theta, and A theta is a unit vector measured from the tip of this vector R in the direction, you might say, as the white parameter moves straight for the plane, the xy plane. Y'all follow me? So it's in this direction. A phi would be into the board, and AR would be in the direction of R, right there. Can you see this, class? I always see this. So just think about this. E is that direction, right? Crossed H, use your right hand. E index finger, crossed in an H, direction of propagation is R, radially away. See how it has to be into the board from in the plane of the board? Okay. Y'all with me? All right, so it's A phi. Now if I've got that, and by the way, I don't know what this value is, but I think I put it down, didn't I? Isn't it, I mean, you tell me, is it 29 naught? So there's a value.
Yeah.
All right. So this is invariant with R. You have a constant value out in front of scalar value. Now what else?
So then ask for the power density for the next part.
All right, just take a moment. I don't want to think. What is power density for a propagating wave? Average power density, better yet.
That's the real part of E cross A.
Well, P ab, now technically you can say it's what? 1/2 the real part of E crossed into H conjugated if it's in the phasor domain, correct? That would be it. But what's the trick here if it's propagating in free space?
Losses.
Yeah, it's lossless, but what are we writing?
1/2 magnitude of E squared over A
Right.
naught.
1/2 magnitude of the actual E field squared, get rid of the phase, over eta naught in the AR direction. Do you agree with that? We'd be propagating the radial direction. Everybody agree? I'm gonna go back over here. For some reason, do not like these markers and their ability. So I'm gonna come over here. I don't know what it is about these, but there's a feel they have for the way my hand writes, it doesn't work out. Anyway, back over here. Use this black one, I can erase it. All right. So we got the H field. Therefore, what is the average power density? If you guys can do this one, I'd appreciate it. It's 1/2, right? Then it's the magnitude of the E field squared. I'm going to do it this way. Well, look at magnitude of the E field squared. I erased my E field, but it's 20 I naught, right? So I'm just going to put this down here. So it's 20 I naught, and forget the e to the minus j beta r because it's magnitude. But you need to remember the cosine of theta. You have to have that, right? And it's squared. So all this is squared divided by eta naught, and it's in the AR direction. Do y'all agree that would be watts per meter squared?
You need the R squared.
Yeah, I'm going to put, you're right about this. It has to be R squared. Thank you. You agree with this? You're absolutely right. Andrew, is this what you're after? All right. Now, that's the power density. If there's going to be a scalar variable, the 20 squared would be 400, I naught squared, what was I naught? 2 or something?
Yeah.
So it'd be 4 times 400 divided by 120 pi times 1/2. There'll be a scalar variable in front of that whole thing. Matter of fact, why don't you do this? Give me this. I'm going to put this down as some k, and it's going to be times cosine squared of theta over. Now use the eta naught in there. So I want just a singular constant out in front, k, and over r squared in the AR direction. Can you give me that constant k, anyone? I don't know what it is.
It was 2.122.
I think I put it down, didn't I? Is it 2.122?
Yeah.
Okay. So it's 2.122 cosine squared of theta over r squared 8r, right? Okay, I got the average power. What next then?
The fourth step is the normalized power density.
Normalized. Normalized power density. A very good question. So what is P normal? It's only going to be a function of angle theta, right? That's the only, normalized power will only be a function of the angle. Will not be a function of radial distance or anything like that. Y'all with me, class? At a constant frequency. So what is the normalized power density? By examining this, what do we need to know? We need to know the maximum possible value for a given R, right? Can you all see it's with the angle theta is 0 or pi? You all see that, class?
Wait, can you say it again?
See that cosine? When is cosine a maximum value? What is the maximum possible value?
Pi.
It's going to be at 0, right? What's the cosine of 0? 1. Cosine of pi, -1. Cosine of 2 pi, 1, right? But the magnitude, because that's a cosine squared, it's either at 0 or at 1, right? And the value is 1. So that means the normalized power, if you take the maximum possible value, or put cosine equal 1, and divide it into that, you just get cosine squared. Do you agree with this, class? So the normalized power, I hope I put that down there. Cosine squared of theta. Now what?
Then ask for the maximum directivity.
All right, how do you get the max directivity? We have the normalized power, right? What do? This is the props, right? This is the whole purpose of that lecture last night.
It was the 4 pi over the solid.
Yeah, do you remember this? Dmax, the greatest magnifying power, I like to say. So that's gonna be what? It's gonna be 4 pi,
Over omega p. I can't remember what it's called.
well, how about, yeah, we just put the
Double
integral in here.
integral
It's the integral over the
P
entire range of a
theta.
normalized power density, but there is a sine of theta times the theta d phi, correct? The limits on this for phi are 0 to 2 pi, which makes it trivial because that's not a function of phi. And for theta, it goes from 0 to pi. Do you agree? I'll put the values in now. Matter of fact, what we'll do is this integral. When I look at the integral from 0 to 2 pi of the integral times the integral of 0 to pi of cosine squared of theta times sine, this was a gimme for a lot of you, d theta d phi, and I'll call that omega sub p. If this is the part you were wondering about, Andrew, just follow me. A lot of you guys have calculators to do symbolic integration. Yeah, this is not symbolic. It's it's a hard limit. You can do this, but you don't need to. If you look at this, first let's do the d phi integration. Nothing inside this kernel of integration depends on phi, does it? Nothing. So if we integrate d phi, we get phi from 0 to 2 pi is just 2 pi, right? So omega is simply 2 pi. And now we've got to evaluate this integral. Cosine squared sine theta, cosine squared theta, sine theta d theta, right? From 0 to pi. Cosine squared of theta, sine theta d theta. Well, how about let u equal cosine of theta, du is equal to what?
Negative sine.
Minus sine of theta,
Yeah.
is that right?
Yeah.
Correct, class?
Yeah.
All right, now what do you see this becoming? Well, this is going to be 2 pi, right? I'm going to leave the limits alone, and that's going to be u squared du, right? But there's a minus sign out in front, nothing broke. It sounded loud.
Sure.
If I had a quarter for every time I drop my laptop off my recliner at home on the floor, I'd probably be able to buy a meal. All right, now you have to change the limits. The minus sign is right here, and I think I mentioned this occasionally. I always circle my minus signs. As the older I get, the worse my eyesight is, so I can miss them. So I always circle, especially if you're using pencil. And please, there's one person in here that writes with a really light pencil. Please use a darker colored pen or something so I can see it. I'm old. All right, so now you see that's theta equals 0, so u would be 1. You agree with this? From 1 to minus 1, and you can see what's going to happen here when I do the integration. You see how I got a negative sign here? I can get rid of that negative sign by taking the 1 and putting it here and the minus 1 in here. Do you agree with this before I even do the integral? Agreed? So let's get rid of this, make that minus, make that plus. So when I get this, you can see what's going to happen. This becomes 2 pi, and then it's u cubed over 3 from minus 1 to 1. So that's really what? 2 pi here, right? And then it's times 2/3, isn't it, class? So that's 4/3, 4 pi over 3 would be the capital omega. Do you all agree with this, by the way? Can you all follow me? Trent? Andrew, you asked it. Do you follow me on this? So what is this going to be?
3.
Well, this is 4 pi divided by 4 pi times 3, or it's simply 3. I hope I wrote that down. Is that right? Now what else?
And then ask for the directivity.
We got the, oh. Okay, so if we have D max, what is the directivity? Be attentive here. There's one more thing I'm going to add if it's not already on there. So now the general form of the directivity that would be multiplying that antenna would be what? Now the directivity is a function of theta, is it not? Right? How do we put D max down, right? Andrew, make sure you see this. Times P normalized of theta, correct? We got D max is 3. What is P normalized of theta?
Cosine squared.
Cosine squared theta, right? Now we got the maximum or we have the directivity, correct? Now what else did I have? There's one part that I'm gonna ask you.
Calculate the total.
PRAD,
Well, how do you get, yeah, that's one of it, we're gonna do that. How do you get total power radiated?
power average of the,
Let me suggest this so you don't fumble the ball. If you're trying to memorize formulas out of Wentworth's book, he has a lot. Here's my idea of the best and easiest way to do it. Look here. You see this equation right here? That's average power, right? Y'all see that? Make sure you see this. All right, now watch. If I want total power, I'm not even going to mess around with some of the formulas. I can do that using directivity, guaranteed. But what I'm going to do is something. I'm just going to go to basic formula so I don't confuse myself. That is the average power density, right? So if I say I want the total radiated power, that would be what? It would be an integral of the power density, which is K times cosine squared of theta over R squared, right? 8R. There is no phase in this one. Then you would dot it into a differential surface, spherical surface. I hope I'm being clear about this. I don't think, did I put down a differential surface on one note, Andrew? There's a differential outer surface for spherical coordinates, right? What is it? Well, it's equal to R squared sine theta, right? It's going to be d theta d phi in the AR direction. Now this is the outer surface if you have a sphere as such. And you're on the outer surface, there's this differential surface here at a constant R that points in the AR direction. That would be the ds. Do y'all follow me on this, class? Did I put that on there in one moment? No. Well, that's something I would give you, but you should become very familiar with it because you're going to use it over and over again shortly. You used it when you did a lot of the problems back in EMAG 1, you used that. Remember this? For spherical coordinate calculations. So it's going to be this, and now this becomes, it will be in the AR direction, and it's R squared, and now it's times sine theta, d theta d phi. Here theta goes from 0 to 2 pi, and from 0 to pi. You can actually see once we do this, the R squareds go. Do y'all follow me on that? Right? And the AR dots, these two dot out, the R squareds go. Right? We just did this calculation. So what do you get P rad equal to? P rad, well, I can take the K out in front, right? There's a K there. Do y'all follow me, class? Can you all see this? I take that out in front. I have K out in front. Now, let me do it this way. I'm going to integrate from 0 to 2 pi. That's the d phi integration. So there's nothing inside, just like before, that is a function of phi. Therefore, when I integrate d phi, I get phi from 0 to 2 pi, simply breaks out 2 pi, correct? And now I'm left with what? Now I got that crazy integral of cosine squared of theta, sine of theta, d theta from 0 to pi. And that's what? K times 2 pi. Do you remember what this is? It is 2/3, right? Do you remember how to get it? Let u is cosine squared. Let u equal cosine. du is minus sine. You go through the thing, right? It's a straightforward integration. You can do it in your calculus if you want, but it's kind of an overkill. I don't remember exactly what K was, 2.12, but now when you do that, you get P rad, don't you? How much was P rad?
8.889 watts.
Agreed? What else do they ask? Remember, we started with the E field. Go ahead.
The last thing they asked for was just the R radiated,
The what?
the R rad.
How do you get R rad? Do you remember the formula I put down?
Yeah, you put it on there. It's
I want to make, this was something I was going to talk about today, and the reason I put that problem down there it lends itself, it just leads you right to the question. So this is how we figure out how much power is radiated by an antenna when there's no ohmic heating. This is where there's no losses. Well, all that power is from something that they term the radiation resistance. The radiation resistance is associated with the electrical transfer, or you might say conversion of electrical current that would normally thermally heat something into photonic energy that's launched. That's important. So this is propagating radiated energy, or power. Here's what I mean. Now, that antenna looks like this. If I have a voltage source here, and here's my antenna, but now I can replace the whole antenna by something that looks like a radiation resistance. That resistance right there will tell me, remember, I know the current going through there, right? 2 amps, I think, right, as a peak value. If I know that, and I know the power radiated, I can figure out the radiation resistance. Just like any resistor, and this is assuming a time harmonic field or a field that's sinusoidally or cosinusoidally varying, the actual power or the radiated power associated with this is equal to 1/2 I naught squared times R rad. Now, do you agree with that, everyone? It's just like, and assume it wasn't radiated. If it was dissipated, then it would just be the resistance, right? It'd be 1/2 I squared R. It's a standard formula that you're very familiar with from circuits, hopefully, right? So I know this, therefore R rad, this is the way you do this. R rad is going to be equal to 2, and it's going to be equal times P rad, right, over I naught squared. And I don't know what that is, but that's how you get it. And it's always going to be gotten that way. What did you get for that, guys? Did I put that down? 4.1?
4.4.
Ohms. What? Anything else? Here, we've got one more for you. Because all the other problems I gave you had this in there. Beam width, right? Half power beam width. Now, follow me. Please be attentive here. Don't mess this one up, because people mess this up all the time. Black does not erase well, that's for sure. But it's easier to write with that black marker. So now, I want you to follow me on this. We got the beam. We know that the normalized power density, this is the key. You could plot either directivity versus angle or normalized power density. It doesn't matter. I prefer normalized power density. And that is equal to cosine squared of theta, right? All right, here's theta. And if you think about this, let's go from minus pi here to pi. Actually, theta typically only goes from 0 to pi because if you spin it in the phi direction, that's the r vector, you'll be able to cover the entire sphere. Do you all agree with this? Let's look at this one. What does it look like? Well, when theta is 0, the normalized power density has a value of 1, correct? You got to plot this thing, agree? And you can see it's a cosine squared. What happens? When does it go to 0? Pi over 2, correct? Does it ever go negative? No. Comes back up, right? Over here, if we kept plotting, would it look like this? Now, here's something you have to appreciate. Beam width requires you find a half power point on either side of the main beam. If I was to actually do this in polar plots, if this was the z-axis, and we were to plot this, it would look like this. Where this would have a height of 1, this would be a height of 1, and the angle would be measured from the z-axis to the radius vector. Do y'all follow me on this? All right, you see how the beam width would be at the North Pole, and the south pole, and it would be identical. Can you all see that? What would the beamwidth be? Well, I know it's 1 there, but for the half power point, I need to find out where it's 1/2. What angle would it be 1/2 at? Well, how about I ask you the inverse question? That's a cosine squared being 1/2, correct? That would be cosine equals 1/square root of 2, correct? What is the inverse cosine of, or what angle gives me cosine of that angle gives me 1/square root of 2? 45 degrees. Right? We're engineers, know that by heart. You with me? So this is 45 degrees, right? But is that the beamwidth? No. Go over here. That's 45 degrees. You all see this? It's like a snow cone. So the half power beamwidth would be 90 degrees. You all see that? That's not real obvious sometimes. People will take just 0 to 45. You all with me, class? But that thing spins. You see that, kid?
If it was a sine, would you do like, I saw like.
Yeah, that's the
so
one we
we do
do.
like 180 minus.
So if it was a sine, right, and this was a z direction, it would look like this, right? You agree? Now, let's assume that, how about sine squared? Right. Let's assume the power, normalized power pattern is equal to the sine squared thing, right? Well, that is going to be 1, right? It'll be at 1 at 90 degrees, right here, correct? So where is it a half power? If that's 1, where is this 1/2 and this 1/2 in radial distance? Where is the cosine squared equal to 1/2? Anyone? That would be the cosine of theta equals 1/square root of 2. Do you agree with that? Where is that? I mean, sine of theta equals 1/square root of 2. Sorry, right? Sine squared equals 1/1/2, then sine would be 1/square root of 2. What value of theta? 45 degrees, right? From here. Keep going, you're not done yet. Where else? 135, right? If you went to 135, but how far is 135 from 180? 45 degrees. What's this angle? 90 degrees. Y'all see that? I hope that's what you were asking. Who asked that? You asked that? Did that answer that question? Are you all following me on this? Now, any other functional form of the normalized power, it doesn't matter if it's cosine to the 8th power. When you plot anything like that, look for the maximum. The maximum value of cosine can have is 1. Where does it occur? At 0 or pi or 2 pi, right? From that point, move off axis and say when this is, whatever the functional form is, 1/2, right? That's the half power beamwidth. Then solve for that angle. That's all you do. And make sure you get it on either side of the peak value. That's my point. Okay? Other questions? Andrew, I hope I got that. Anything else? Now remember this much. A lot of this stuff requires you to just be clear-headed. Don't be distracted. Don't have a million things in your mind. You'll confuse yourself. It's very simple. Just stay focused on this. And I can't sometimes explain in words what I'm really trying to say because it's hard to, but I can see people all the time second-guessing themselves. Well, it can't be that easy. Oh, it must involve that. There's a parameter there I haven't used. They'll find some way to mess up the problem. It's straightforward. Y'all with me? I hope I made it clear. Okay. So I covered radiation resistance just by happenstance by using that as an example. And now, this is chapter 8 stuff. Let's show you some stuff. Usually, after we talk about beam, we talk about what happens, how do you get the actual radiation pattern of a short dipole. He introduces something called a magnetic vector potential. This is something you're not going to appreciate fully right off the bat. But you do appreciate voltage, right? I mean, at least what's the one benefit of calculating the voltage from a charge perturbation or a bunch of charges compared to calculating the electric field at a point, say statics, electrostatic field. There's one big advantage to the voltage. I want you to just think about it.
It's not from here.
Well, If I have a charge Q, it doesn't matter how many charges, right? I could have a whole bunch of charges, say Q1 and Q2. If I wanted to calculate if that's R1 and this is R2, if I wanted to calculate the electric field here, total electric field, I would say I'd find the electric field from the first charge and the electric field from the second charge, and they are vectors, so they generally have 3 components. And I'd have to calculate that. That's 3 components for this one, 3 components for this one, right? Then I'd have to vectorially add them up, right? But if I wanted the voltage at this point, if I just wanted the voltage here of R, or voltage at the point, it could be R theta phi, it doesn't matter. R theta phi, it really doesn't matter at this point. To get the voltage, well, if we assume the voltage at infinity is 0, which is a legitimate assumption if it's a finite amount of charge, we find the voltage from this one, which is just what? Q1 over 4 pi epsilon naught, and it's just the magnitude of R1, no vector. And then the voltage from the other one, Q2 over 4 pi epsilon naught, magnitude of R2, right? Now you would have to have R as a variable that could vary with position. This is the thing. And it could be an angular function too. But once I had that voltage to get the electric field, if it was electrostatics, it would be just minus the gradient of that voltage. That's a couple of derivatives. It is usually, in general, much easier numerically to calculate a voltage from a static charge distribution at a point, and then go ahead and get the gradient of that voltage to get the electric field. Throw a minus sign in front of it. Y'all with me? It's much easier, really. So there's another type, and that's using what's called a potential. A voltage is a type of potential to do work. That's an electric potential. There's also it's called a magnetic vector potential. But this is a vector, but it's a very easy vector to deal with because it only has one component. If the current only has one directional form, one direction, if it's associated with like a straight wire antenna. I'm going to show you this. This is interesting. So, and this is in just section on short dipoles in the book. If you come down here and you have a current I, call it I naught, assume it's constant, and this wire has a length L as such. We talk about actually make it DL, it has a differential length DL, which would be in this direction, call it DL. So it's got a length L, and it's got an actual vector direction DL, and I'm just having it going up here. Put it at the origin. Are you with me, class? Now, if I come a distance R away, I can say that this will give rise to something called a magnetic vector potential, and the symbol is A. In this case, let me come over here and try to do this a little better. So I'm going to say I have a current I naught, and the direction is going to be DL. And let's assume this is differential, so it's just got a differential thickness. Put it at the origin. Then I come out a distance R here, and I'm going to have something where I have a magnetic vector potential. The symbol is A, but this is going to be a differential magnetic vector potential because this current element is a differential length. You all with me? It's like a differential charge dQ gives rise to a differential voltage, dV. dA, and it's in this book somewhere, but it's not done in the way I like it, is just going to be mu naught over 4 pi, and then it's going to be equal to I causing this, which is I naught, it could be I naught dL, and then there will be a division by R, so it's divided by the actual value of R, magnitude of R, and then there's going to be e to the minus j beta R, but it will be in the AZ direction. I'm going to have to explain this. So So say this is the z direction, all right? The magnetic vector potential, we're going to use this to calculate the fields in a second. You all with me? The magnetic vector potential will always be in the same direction as the current element causing it. So here's a differential current pointing up. You'll notice how this vector potential has the AZ direction because the current's pointing up. If the current was in this direction, if it was IDL, and say that's the AX direction, so say this is I dx AX, that would be the DL there. Then if I come out any distance away, the actual magnetic vector potential would be in that direction. This is very important. It has one directional component associated with the direction of the current. Y'all with me? We're sticking with Cartesian coordinates for this one. So if I have that, here's the relationship between A and B. And it's in the book, but Dr. Wimmer's book will say that the actual curl of B, I think he says it this way, is equal to A. And he has this kind of a confusing way in his book, if I want to. And this is, let's see here. He has a very interesting way there. If you look on page 438, equation 8.26 is what I've got. And he goes through a little discussion, but I'm going to get to the point. Can you all see that? It's equation 8.26 on page 238. Please follow me on this one. So this gets really interesting. Now, if that's the case, you'll follow me on this. Well, B is mu H, so it's really mu 0 times curl of H would be equal to curl of A. Are you with me? Or I'm sorry. Let me get this. Actually, I stated it wrong, guys. I'm sorry. It should be B is equal to curl of A, my bad on this one, which is equal to mu times H. That's what you should see in 8.26. Do you see that? Class?
Yes.
All right. I'm sorry, I had to curl that backwards. That means H itself is equal to simply 1 over mu curl of A. Now, having said a different way, if A was a differential, the differential H field here would be equal to 1 over mu, and it would be times the curl of the differential magnetic field. He doesn't have this way in his book, but it should make logical sense to what I'm stating. Does it? Now here's the way we deal with these problems. If I got a little short chunk of current here, there is a phase here that has to do with time delay. Either you're going to have a phase change at this point of the magnetic vector potential associated with the current, or there will be a time delay if we wrote it in the time domain. You all follow me in this class? Now, if you look at this right here, if that's dA, if I wanted the magnetic vector potential, I would take a curl of that, and I get the differential magnetic vector potential. Agreed? Don't worry about it. I'm going to in a second. But also, I can say that, and it would be, we're going to only care about the far field. If I take a curl of A, I get this. But then if we go to the far field, we don't have to do it this way. I'm going to do it 2 ways, and I'll explain why. All right, that's H, right? That's guaranteed H. If that's A, that's the magnetic vector potential. By the way, that works for near field and far field, what I just wrote there. This is H. Well, if I have H and I wanted E, and we'll assume it's a lossless region of space. Then if I want the E field, I can say, just think about the equation. Curl of H, normally it's J, which is sigma E, but if it's lossless, we ignore the sigma, right? Then you would get J omega epsilon times E. That would be Maxwell's equations. It would be Ampere's law. Isn't it, class? We could get E by saying I have 1 over j omega epsilon, and it would be dividing into curl of H. Well, curl of H is that. So then you could say it's equal to 1 over, and this would be j omega mu times epsilon. There's a mu there. And it would be now times curl of A. Can y'all follow me? I know this math doesn't mean a whole lot to you right now. Well, this curl of A can be broken up as gradient times the divergence, the gradient of divergence of A minus del squared A. This would be at a higher level course we do this. And we will find solutions where we have what are called gauge conditions on A. We set A to have, the divergence of A to have certain values so that we can separate some equation. He doesn't do that in the book, so I'm going to get to the point related to the text material. If I come here, here's the thing. If I have A, I can get H just by doing a simple curl. You with me, class? Now, once I have H, I can assume I'm in the far field, and I can get E just by taking H divided by, or H times eta naught, and then using the proper direction, because I know it's propagating radially away. Do you all follow me? The thought process is, why make life tough by taking another curl if you don't have to? Okay. A lot of this, guys, sitting where you are, I'm thinking about how you're taking it. The first times through, it's going to be hard to really appreciate this. You're going to have to take some of this on faith, but as you work with it, you'll see why it's so valuable. So now, getting back to this, here's some stuff we're going to do. It's in this book. What we need to do is I'm going to go ahead and say, if that's the differential magnetic vector potential, I want to get the differential H field. You all with me, class? So the way I'm going to go get it is, first, I need to get rid of this. This is not a spherical coordinate. AZ is in Cartesian coordinates or cylindrical, right? That waveform has R, and R is spherical. Can you all follow me? So, and this is the way he does it in his book. What I'm going to do is I'm trying to show you this in a way that's not going to confuse you. So if I look at AZ, say I'm at a given angle theta, and I look at AZ, AZ would be in that direction, right? Now the projection of AZ onto the into the AR direction, can you all see how this would be theta as well? If this is vector R. Can you all follow me on what I'm doing here? If that's the z-axis, that's measured R, that would be theta. And therefore, if this is a unit vector, AZ has unit vector, the actual AR component of that, we're going to take it and project it on the R-axis first. This would be what? Well, that would be the cosine, right, of theta AR. Do you agree with that? In other words, AZ itself can be thought of as cosine of theta AR. Now, here's the hard one. When you look at this is a right triangle here, but the A phi direction is orthogonal to this, but A phi is A theta, pardon me. A theta is in this direction. Can you see that? Think of this as the wiper arm, right? If I have my finger in this direction, right hand, just take a look at this. I'm pointing in that direction. As I move down, A phi would be in this. If I'm at 90 degrees, is minus AZ. If I'm at 180 degrees, it's minus whatever that axis is, AX or AY. Can you all see that? So that means the projection in the theta direction would be minus the sine of theta, A theta. Now he should have that in his book. Hopefully I can tell you where it is. But this is one of the things, a lot of times you're going through this, you don't see, where we got that? Oh, okay. That's on page 442, right above equation 8.44. I want to tell you what I'm showing you now is stuff that will, if you just read through that, you're going to get confused in my opinion. Some of you may not. So now I replace this with what I've got over there. You all see that? So now I say, well, that means my differential A field will be equal to H, so differential magnetic vector potential, and I'll put it here. I want to make sure I'm trying to be as clear as I can about this. dA here is going to be equal to mu 0 over 4 pi, and now it's going to be I naught dl, just the differential length, and actually this is going to be a scalar because AZ takes care of that. So it's differential length, and then it's going to be e to the minus j beta r divided by r, but here's where things change. So now I have this should have been AR here. Now I have cosine of theta AR minus the sine of theta A theta as dA. Can you all see that? And he has that. He's going to show you what in equation 8.44, he doesn't put the differential there. He puts the whole thing. And now, in order to get the actual differential H field, that's going to be equal to, and that's over here. It's 1 over mu curl of the differential A field. So it's 1 over mu. Just work with areas and I'll be done. Now I have to take the curl of that. So I can take the mu 0, you can see mu 0 becomes a non-item, over 4 pi. You have I naught coming out. And with dl. dl in here. That's this part, and now we have to take the curl of this. Now, if you want to know how to do the curl, you can see you have both R and theta components, right? When you do the curl of this, you in general are going to get several components. You're not going to have just one component, but some of them are near field, some of them are far field. I know you want the quiz. At the end of the day, we'll do the near field stuff next time. The actual value, the H field that you get is going to be on equation 8.49. So what actually happens is, if you do this differential H field, you're going to come up with something that's going to have differential H field itself. It's going to be J beta I naught times differential length, dz in this case. And it's going to be over 4 pi. And then you're going to have R here. It's going to be times e to the minus j beta r, and there'll be a sine of theta, and it'll be the AP direction. I don't have time to do this right now, but if you integrate this thing over the length, you end up getting an H, or let me just give you the E field. The E field, the far field for this differential length current right here. I'm about out of time. Is going to be equal to J, A, this is the one you remember, B, and then it's times the length of this, the differential length, or the total length, now L, and it's going to be times the sine of theta times e to the minus j beta r over 4 pi, where he has our things, leaves it 4 pi, I'm not sure. Yeah, he leaves the 4 pi in there. 4 pi r, you don't have to have a 4 pi in there, you can actually get rid of some of the stuff with beta and beta, but he has it over 4 pi r. And then it's going to be times I naught on top. And it will be in the A theta direction. So that's the E field from a short dipole. I didn't have time to do the whole curl of this thing. I will next time. I'll at least show you. Once you get the H field, the differential H field, be integrated over the length, it just brings this, instead of dz, we're going to get L, the length of that thing. And once you have that, the H field, you get the E field. If you're in the far field, that's what you're going to get. You might want to make a note. This is far field. And I know you want your quiz. I think I get about 15 minutes on. All right, so how about we spread out? Let's see.